Hello, this is video 3, another one on torque. And in this case, we're going to consider when we are not in equilibrium. So let's remind ourselves of what we did with linear forces and linear acceleration in our dynamics unit, which was unit 2. So we learned that the net force, a net force, causes linear acceleration. And in your reference tables, it's phrased like this, that the linear acceleration is inversely proportional to the mass, or the inertia, of an object, and directly proportional to the net force. Inertia being this property of matter really similar to mass that resists changes in motion or resists acceleration. And we had problem-solving strategies. We drew a free body diagram that showed all the forces acting on an object, typically from the center of mass. We asked ourselves the question, is it accelerating? And we drew that into the scenario. And then we used the best equation ever, the sum of the forces equals ma, to solve for whatever was needed in the problem. And that got more complex with friction and things at an angle, but that was the general problem-solving strategy. And we're going to apply this here with torque. Let's just remind ourselves that torque is also Fr, so we can find the net torque on a disk if we have forces acting at different radii from the disk. So I've already done this with the class up. You can pause this and try it, or just listen as I talk through it. So the sum of the torques, or the net torque, would be the sum of every force times the distance it acts from the radial, or from the axis of rotation, as long as the force is perpendicular to the axis of rotation. So if we look at each of these forces, or perpendicular to the moment arm, the radial line that extends from the axis of rotation to the point that this force is acting. So this F1, this 10 Newton force, is perpendicular to the radial line. F2 also perpendicular to the radial line. And even while they drew in these degrees here, F3 is still perpendicular to this radial line. So we don't need to account for the angle that they've labeled there. So what we'll do is just remember that our torques that turn it in the counterclockwise direction, we're going to define as positive. So this 10 Newton torque we would call negative. So negative 10 newtons times the radius there, which I asked a random number from the class, and we got 10 centimeters, so that would be 0.1 meters. So we would then add the torque from the next force, so 9 newtons times the 0.1 meters. But that's still going to go in the negative direction, so we would show that with a subtraction. And then the F3 is going to twist this whole system, if it's all connected, in the counterclockwise direction, so that would be given a positive sign, so 12 times this other random number, 5 centimeters, 0.05. So we would just add all those up, accounting for the direction. So that's an important point, whether you're doing rotational forces or linear forces, making sure that these vectors have their directions accounted for properly. So that's one way to find the net torque. And the other way to find the net torque is to use Newton's second law in the rotational frame. So a net torque causes an angular acceleration. The same equation really we're seeing here, while this looks a lot like an A, it is an alpha, but this is the text and the font that they use on your reference table, so you want to keep a close eye on what that is. It's alpha, not A. So the angular acceleration alpha is inversely proportional to the inertia. And in the case of rotating objects, there's a property of a rotating object called the moment of inertia, or the rotational inertia, as it's phrased many times. And it has units of kilograms times meters squared. We'll talk more about this in just a second. So the angular acceleration is inversely proportional to the moment of inertia and directly proportional to the net torque, or the sum of the torque. Really, the idea with moment of inertia is objects with a larger moment of inertia have a harder time accelerating in an angular way. So moment of inertia is really like mass, or rotational inertia is like mass, However, it takes into account how the mass is distributed throughout an object. The generalized formula for the moment of inertia is the sum of every little mass chunk. So if I have a little mass chunk here, times the distance that mass chunk is from the central axis or the rotation axis squared. So it depends more greatly on how far the mass is from the rotation axis and less on the mass. Now, we would add all these up to get the moment of inertia of a particular object. We don't use this generally, but the moment of inertia of a point mass is just mr squared. So it is good to just think that generally moment of inertia is mr squared, but for different shapes, it has different values. So there's like a chart here that tells you, and I gave this to you on your homework, and it's on page 210 on the textbook, of the different shapes and their moments of inertia. So we can see the hoop with all of its mass outside has a larger moment of inertia than a disc where it has its mass distributed evenly from the center to the outside. Even smaller is a solid sphere, and bigger actually is the spherical shell. So bigger than the disc, but not as big as the hoop. So let's look back. So if we think about this playground ride, if all of the people on the playground ride are out on the outside, it's harder to get this thing turning than if all the people sit on the inside. So with the mass close to the center, it has a lower rotational inertia or lower moment of inertia, and it's easier to get it accelerating, easier to turn it. So the big idea is that a net torque causes an angular acceleration, and we need to shift a little bit the way that we draw forces for rotation, because we're interested in the torque, in where the force is acting from the rotation axis of the object. So if we have a ball or a sphere sitting on a ramp, the forces that act on this would be the normal force perpendicular to the surface, so that acts at the point of the surface, perpendicular to the surface. We've got the force of gravity, which acts from the center of mass straight down, and then the force of friction acts opposing motion, so that goes up the ramp, and that is what's going to cause a torque and cause the ball to rotate, because this force is acting perpendicular and at a distance away from the rotation axis. So Fg does not cause a torque, it's acting right at the rotation axis. Fn does not cause a torque because it's acting parallel to the radial line there. So they would, Fg would, however, contribute to the linear acceleration of an object as well as Ff. So the part of Fg that points down the ramp plus the Ff, which points up the ramp, so we would call that negative, would contribute to whatever linear acceleration this object has. But if we think about the angular acceleration, we want to think about the torque caused by the force of friction. So this is a practice problem. You could pause here and kind of look through it. It starts with rotational motion. So if I get this bicycle wheel spinning with an angular velocity of 2 revolutions per second after applying a force perpendicular for 0.5 seconds, what acceleration did I give the wheel? What angular acceleration did I give the wheel? And there's a couple ways to do this, but the way that I did this was I wrote down what was given in the problem, good steps for success. So the radius of the wheel was given in the problem, the angular velocity that it reached, 2 revs per second was given, but we need that in radians, so I just multiplied that by 2 pi, because 2 pi radians is 1 complete revolution. So 4 pi radians per second is the final radial velocity after the time of 0.5 seconds, and it started from rest. It has an initial angular velocity of 0. So looking for that angular acceleration, which is just the change in the angular velocity with time, it would be 4 pi over 0.5 seconds, so 8 pi radians per second squared. So what torque did I give this wheel if we say the wheel has a mass of 1 kilogram? So we'll look up the moment of inertia of a wheel. So we'll look here and we'll say, well, a wheel's kind of like a cylindrical hoop. rotating about its center, so that has a moment of inertia of mr squared. So we'll find the net torque by taking the moment of inertia, mr squared, times the angular acceleration, which we just calculated. So 1 times the radius, 0.32 squared, times that angular acceleration we found. And then what force caused this torque? Well, now we're going to kind of work our way back to remembering that the net torque is also equal to Fr. So the net torque we know, the radius we know, we're looking for the net force. So the net force would just be the net torque divided by the radius, or 8 newtons. So we need to be flexible in using rotational kinematics to think about the angular acceleration, and in using the idea that torque is I alpha, but also torque is Fr. And that's it for torque and angular acceleration.